So today's theorem is that the space of continuous functions from the unit interval 0, 1 to the real line is a complete space with a sup norm. What does it actually mean? Okay, first of all, recall what this is, right? This is just a set of continuous functions with domain 0, 1 and range R. And we know this set can be endowed with the structure of a vector space. There's a natural zero element, which is a function constantly equal to 0. There is an operation of adding up elements. There's multiplication by scalars. They satisfy all the properties that are required of a vector space. So in this sense, C is a vector space. The space has a norm, which we define and analyze in class, which is the sup norm. I can compute for each function f in C its supremum over the unit interval, or rather the supremum of its absolute value. The supremum is finite because f is continuous and therefore bounded over this compact interval. And therefore, this definition makes sense. It gives us a norm. What is being said here is that any sequence that is Cauchy with respect to this norm has a limit also with respect to this norm, and this limit is an element of C, right? So Cauchy, to remind you, means that I have a sequence of functions such that if I look at a distance between f sub n and f sub m, this distance, according to the infinity norm again, goes to 0 when both n and m go to infinity. Or if you prefer, you have a net with definition of epsilons, which is for any epsilon, there exists a naught belonging to n, such that if both m and n are greater than or equal to a naught, then the distance between the terms of the sequence corresponding to n and m is less than or equal to epsilon. From this alone, we will have to find a limit for the sequence f sub n. Okay, one remark before we start. This definition of the sup norm, it makes sense for any function from 0, 1 to r. If you allow for an infinite sup, right? If f is unbounded, it could be that this is infinite. Well, actually, if it's unbounded, then this is certainly going to be infinite. If f is bounded, this is finite. So this makes sense for any function f. We don't need to know that the function is continuous. So use the symbol as long as you understand its limitations. Now, the second thing is about the actual proof. So how we're going to try to prove this, or actually succeed to prove this. So I'm going to assume the whole time that we have fixed a sequence that is Cauchy in C in the sense of this definition. And here's how we proceed from there. First of all, okay, so the limiting function I'm going to call f. And I'm going to say, let's find f via pointwise limit. So what do I mean by that? We define in class what the pointwise limit of a sequence of function is. It's just, instead of requiring that the functions converge in the strong sense, here all I have to show is that there exists a limit of f sub n of t for each t. Okay, what this is saying is the following. As I said, we need to find a limit, right? We need to prove that the sequence has a limit. At first sight, it's not obvious how you go about trying to find a candidate for the limit, but it turns out there's a natural candidate in the sense that we know, when we're going to prove that, this limit exists for all t. So I can define a function, right? So for each t, I have a uniquely specified value, which is the limit of f sub n of t. This is a real number, and that by definition is the value of f of t. So this specifies a function. What is left to be done from this point on is to show that you have okay, so the outline has 3 parts. I still need to prove that this limiting function is continuous and that the sequence f sub n converges to it in the sup norm. So next step is going to be to prove a uniform limit, which is to say that f sub n minus f infinity goes to 0 when n goes to infinity. The third and final step will be to show what people usually paraphrase as saying that the uniform limit of continuous functions is also continuous. So the third step will be to show that step 2 implies f belongs to C. And these three steps together finish the proof. In step 1, I show that it exists in the function f, that's the pointwise limit of the sequence f sub n. Step 2, I show that the convergence is uniform. Step 3 shows that f is actually a continuous function. So what we have shown is that just starting from this assumption, we can find a function f that is continuous and is the limit of the sequence f sub n according to the sup norm. And that's what we have to do, and that's what I'm going to do right now. Okay, except that I'm going to have to raise a few, at least the third box. So we're going to do steps 1 and 2 more or less in tandem. And then we're going to move on to step 3. Okay. How do we prove statement 1 here? So again, the statement is about the existence of this limit for each t. Okay. Right, so for each t in 0, 1, I have that f sub n for all m and n. Well, m and n are naturals. F sub m of t. This is sandwiched between two things. Let's take a look at this. This is the difference between f sub n evaluated at t and f sub m evaluated at t. On the one hand, I'm saying that this difference, when I take the absolute value, is non-negative, and that's obvious. On the other hand, I'm saying something slightly less obvious, which is that this difference is upper bounded by the supremum over all possible t, not just this t, of the difference between f sub n and f sub m. And that's the sup norm. How is this useful? Well, this thing here goes to 0 when both n and m go to infinity. That is what's over here. So we have a sequence of reals, right? Well, doubly indexed by n and m, which lies between 0 and something else that goes to 0. So it's sandwiched between two things that go to 0, and therefore it goes to 0 itself, meaning that lim m n going to infinity, f sub n of t, f sub m of t is 0. Which is the same as saying that f sub n of t, which is a sequence of real numbers, is Cauchy. Right? This is what Cauchy means. It means that I have a sequence of values indexed by n, and I'm saying that the difference between terms in the sequence goes to 0 when the two indices go to infinity. So this is Cauchy. And therefore, there exists the limit f sub n of t, which is what we call f of t. So there's no big deal here. Right? So again, I wanted to prove the existence of a pointwise limit. So what I did was I took a t. I showed that the sequence of values f sub n of t is Cauchy by this calculation. And once I know it's Cauchy, I know it converges because it's a sequence of real numbers that's Cauchy, and all such sequences converge. And the limit is what I call f of t. Okay, so that's it for step 1. What about step 2? Well, it sort of follows from the same calculation. So let me try to reuse what I wrote over here, at least partially. So I'm gonna, so of course this is still true. And now I know, okay, so I know this thing here. Let me write it with m replacing n. It really doesn't make a difference, right? It's just like a dummy variable. Good, because now I can take a limit when m goes to infinity. Notice, when m goes to infinity, this goes to f of t. And for the time being, is going to be fixed. So m goes to infinity. Fm of t goes to f of t. And by continuity of the absolute value of the sum operation, if you like, this thing here converges to f of t. What about this thing? Well, this is still 0. What about this thing here? Well, I don't know that it converges, right? So I need to be a little bit careful. However, what I can say is that this is less than the limit superior, or lim sup, fn minus fm infinity. Okay, now what, right? Notice that what I wrote over here is valid for all n and all t. So in particular, I'm going to take the sup over t here. And I'm going to conclude the following. That the distance between f sub n and f in the uniform norm, or the sup norm, which is the supremum of these expressions, well, so this is upper bounded by this thing, which doesn't depend on t. So this is an upper bound for the whole set of these values, and therefore the supremum is less than this upper bound. And of course, this is greater than 0. Remember that my goal is to show that this goes to 0. And again, I have this sort of standard situation where I have it's lower bounded by 0, it's upper bounded by something. So if this something goes to 0, I'm done. But how do I prove that this goes to 0? Well, there are so many ways that I could spend the rest of the day telling you about them. Let me show you just one. Okay? My claim is that if I take, in particular, let's look at this thing over here. If I take n greater than n naught, I know that this lim sup, this is a claim, right? I need to argue why that's true. Okay, why is that? Well, okay, take n greater than n naught of epsilon. I know that once m is also greater than n naught, then the distance that's over here is less than epsilon. Well, I mean, this is not valid for all m, but it's valid for all m that are large enough. And we know that here we have a sequence in m, right? M is changing, n is fixed. And I know that once m, this guy over here, is large enough, this difference is less than or equal to epsilon. Here's another fact for analysis over the real line that's very important, and we're going to use it here. If you have a sequence indexed in this case by m that is less than or equal to epsilon for all m that is large enough, then its lim sup is less than or equal to epsilon. You cannot have an accumulation point that's greater than epsilon. Once we know that, then we know again this is less than or equal to epsilon for m large enough. Therefore, the lim sup is less than or equal to epsilon. And then we have this bound here, right? So we have that f sub n, well, it's greater than 0, sub epsilon minus epsilon. And this holds for any epsilon that we choose once n is large enough. Therefore, it has to be true that this goes to 0, right? Okay, so this is it for steps 1 and 2 in our proof. Right, and now we're gonna need more space to prove step 3. So bear with me as I erase this makeshift blackboard, which is actually a wall in my kitchen. Paint it with the right kind of paint. This is a wall that my kids sometimes like playing with, except that for these next few days, I'm gonna be the one playing. Maybe the next several days, I don't know. Right, okay, so now we're gonna do step 3. So let me rephrase step 3 here in a way that's more in keeping with what we want to do. So here's what we know. Fn converges to F pointwise and uniformly. And Fn converges to C for all n. And from that, I want to deduce that F itself is continuous. So what do I want to prove? So what is continuity of F? It means that if I take a sequence, which I'm going to call T sub j, in the domain of F, and if I take a T also in the domain, if T sub j converges to T, that should imply that F of T sub j converges to F of T. Right? This is what continuity is. So what we want to prove here is that F belongs to C. So I'm going to fix a sequence like this. I'm going to fix T. I'm going to assume that T sub j converges to T, and I'm going to show that this is true. Okay, how does one do that? Right? The point is that we know that this property is true if we replace F by F sub n for any n, right? So F sub n is therefore F sub n of T sub j converges to F sub n of T. Great, but how do we use that, right? There's an issue involving double limits somehow, which is that I have to take, I know that once n goes to infinity, I go to F. I know that if I keep n fixed, then and I move the j, then everything works. But how do I combine the two things? Well, okay, let me do the following. Well, here's a way to do it. I'm gonna try. I want to compute this difference, and I'm gonna try to compute it starting right. So I fix n for the time being. So let me say I'm gonna fix n in. I'm just gonna try to write this. Okay, let's go to this kind of world of wishful thinking where we replace F by F sub n. And now we need to come back to the real world. So there's a bunch of terms that I'm gonna add and subtract here. Sorry, this is inside the absolute value, right? So F sub n of T minus F of T. And right now I have an equality, right? So I just did, okay, I add F sub n of Tj and I subtract the same quantity. I added this guy and I subtracted this guy, then added it. So this gives me a 0, this gives me another 0, and I'm left with the original terms, which are over here. Now I'm going to use the triangle inequality because I want to write this thing in terms of f sub n of tj and t. And now I need to do something. Okay, I'm just going to say the absolute value of this is less than the sum of these three absolute values. But what about the other two terms? Okay, this guy here, I know that goes to 0 and goes to infinity. So in some sense, if I want to compare this to this, I'm in good shape once n is large enough. This is going to be small. This guy here is a bit more, right? Why do I know this is small? Because there's a pointwise limit. I know that f sub t goes to f of t. This guy is harder to deal with because I have both n and j changing. And that's a double limit issue that I was alluding to earlier. However, and here's the main thing. Here's what we're going to use uniform convergence. I don't really need to know anything about the relationship between j and n. I can just say, okay, this thing here, I can bound it by the sup. I'm just going to take the sup over all possible points in the unit interval. And just going to say that this whole thing is bounded by the sup. So I'm just going to say, let me write this preliminary step here first. And let me just say then that this whole thing is upper bounded by this difference. Plus, I'm going to bound that by the sup. And this I can bound by the sup as well, so I get twice the sup. So now we're in business. So let's see if we all get this. This difference, I really wish I could replace f by f sub n. Of course, if I try to do that, there's a price I have to pay. But in terms of upper bounds, the price is this. So this difference is less than this difference plus twice the sup norm. Okay, so let me rewrite that because you're going to need more space. So here's what we have shown. And let me put this over here, and let me say that this is less than f sub n of tj minus f of tj of f sub n of t plus 2 f sub n minus f. And this is valid for all n. And this is very important. Now, there are different things you can do to finish the proof once you get to this point, right? We want to prove that this goes to 0. So we better prove that this thing goes to 0 somehow. Thing number one is you can say, well, I first take n large enough so this is very small. And then given n, I take j large enough so this is very small. And therefore, I have something very small on the right-hand side. I'm going to do something that's slightly different in spirit, though it boils down to the same properties. I'm going to use lim sups again, since we talked about them, right? I'm going to fix an n, and I'm going to take the lim sup here. As I mentioned before, if I have two sequences, and sequence 1 is upper bounded by sequence 2, then the lim sup of 1 is upper bounded by the lim sup of 2. So I know that the lim sup of this is less than the lim sup of this when I'm taking lim sup in j, and this is important, right? What's the lim sup of this thing? Well, here there's no j, so this term is going to stay the same. Here, however, we know that this thing, right? So let me write it. Like this. This thing, okay, I have a lim sup, but I don't really need a lim sup. I know that f sub n is continuous. Tj converges to t. Therefore, this has a limit, and this limit is simply 0. right? So let me get this term out of the way and just rewrite this as just say this is at most twice the norm. Now this holds for all n. And I can now send n to infinity in particular, right? I have complete freedom in how I pick n. Once I take the lim sup, kind of the difficult term, which is this one, has completely disappeared. Once I take the lim sup in j to be specific, right? This term disappears, I'm left with this guy. And now I can send n to infinity. Here, this doesn't depend on n. This does, but it goes to 0. And I get that the lim sup is sandwiched between 0 and something that goes to 0. Therefore, I have that the lim sup is 0. But now look, this is a sequence of no negative real numbers. If I want to prove that this sequence goes to 0, right, the sequence of the absolute value here. If I want to prove that this sequence goes to 0, all I need to do is to prove that the lim sup is 0. Why? Because if the lim sup is 0, then I know that the sequence has no negative, so the lim inf, right, this smallest accumulation point, is also larger than or equal to 0. So the lim sup and the lim inf are equal, and therefore the limit exists, and therefore we have proven this, right? We're using the fact that there's no negative to say the lim inf is greater or equal to 0. The lim sup is 0. Therefore, lim sup and lim inf are equal, and both are 0. The limit is 0. And now we're done, because remember, what we wanted to prove is that when t sub j converges to t, f of t sub j converges to f of t. And this is how we accomplished it. We said, let's compare what happens with f, then with what happens with f sub n. This thing we know behaves well for f sub n when j goes to infinity. And all we need to check is that the difference between doing things with f and doing things with f sub n is uniformly bounded. If we have a bound that doesn't depend on j, and this bound goes to 0 when n goes to infinity. And that's how we deal with this issue of double limits. Basically, we don't do a double limit. We first do the limit in j, and then we do a limit in n. And that's it.